All right. Hey, it's your old pal, Mr. Cook. This is our last video going over number 24 and 25. So both of these have to do with motion, it looks like. So we got to remember like one key thing, and that's the relationship between position, velocity, and acceleration. So if you have position, like where something is, if you take the derivative of that, it gives you the velocity. If you take the derivative of velocity, that's going to give you the acceleration. Okay, and that's what we learned like last chapter. Okay, but you can reverse that process as well. So if I have antiderivatives, right? Like so, if I take the acceleration function, for example, and if I take its antiderivative, so just integrate it for t, that function that I get is the velocity function. Because remember, if I take the derivative of velocity, that gives me acceleration. So antiderivative of acceleration gives me velocity. Similarly, if I were to take the velocity function and take its time derivative, that's going to give me the position function back. And usually you won't have bounds on this stuff, so you'll have like some constants. But if you're given an initial condition, you can solve for what that constant is going to be. Some other things to note while we're talking about position and stuff like that are the following. If I want to find displacement, so that's like a special phrase, displacement. It's basically like how far you've gone from your initial point to your ending point. And that comes directly from this function right here, because displacement has to do with f of x. So basically, like if I want to find out where I am from point A to point B, it's just the difference in the position. So that's just the integral over some boundaries. So from A to B of your velocity function. And that's different from finding the distance that you've traveled. Because imagine this is like a pedometer, and it just like monitors how many steps that you've taken. It doesn't matter if you're moving forward or backwards or anything like that. So the distance is like your total steps that you've taken in some direction. Well, I'm sorry, total steps that you've taken regardless of direction. So you can do the same thing. It's the same thing as the velocity function, essentially. The one difference, since direction doesn't matter, we're taking the magnitude of it. In other words, the absolute value of the velocity function. So just know those ones as well, and that should serve you pretty well. We're not necessarily going to use all these in this problem, but those are all good to know. Okay, anyways, so after that brief little review, the rest of this should be pretty easy. All right, so for part A, well, let's read the problem. A hot air balloon rising vertically with a velocity of 16 feet per second releases a sandbag at the instant when it is 64 feet above the ground. Find the velocity of the sandbag, and then find the height, like when the sandbag is above the ground for any t value. So let's try out a little scenario here. Here's my little hot air balloon. Okay, and then let's see here. So it has a sandbag attached to it, and if the sandbag is released, then like if this thing is going up, the sandbag initially is going to be going up as well before it like starts to go down, right? Like, and you've probably seen this. If it has momentum, if it's going forward, it's going to maintain that momentum until the velocity is kind of all eaten up. Then it's going to fall afterwards. So that's kind of what we're dealing with here. Okay, so even though it says that the hot air balloon is rising at a velocity of 16 feet per second, technically that's the same thing with the sandbag. Sandbag's going to have that exact same initial velocity. Yeah, so let's like write some of that stuff down. Just some initial conditions for this. So I know the velocity when the sandbag is released is going to be equal to 16 feet per second. And then also I know that the sandbag is released 64 feet above the ground. So that means that the initial height or position of the sandbag is going to be 64 feet above the ground. The last thing that I have to worry about is something that's implied here. Since it's rising vertically, the only thing acting on it, the only acceleration acting on it is gravity. So what I do is I write out the acceleration function as well. Acceleration is going to be constant. And for feet, when you're talking about feet per second, right, in US standard measurement, the gravity is approximately negative 32 feet per second squared. So just be aware of that. Like, kind of remember that one. And then if it's metric, instead. So if it's using like meters and stuff like that, then it's going to be the acceleration is 9.8. 9.81. I don't remember if like we use 9.81 or 9.8 in the notes, but 9.81 meters per second squared. So be aware of that. Like know those two because they're very helpful when you're talking about vertical motion. It's really helpful for part A because that's going to help us to find the velocity of the velocity function for this object. So the only thing that's acting on this thing right now is gravity. So that's an acceleration. And if I want to find the velocity function, remember that velocity is equal to the antiderivative of acceleration. So that's what I'm going to end up doing here. So there's no acceleration. I can find the velocity function from that. So I know that the acceleration due to gravity is just negative 32 feet per second squared. So if I take the antiderivative of this thing, I'm going to get negative 32 times t. But then since it's an indefinite integral, I'm going to be adding on some constant at the very end. Now that usually would be where we would stop, right? But we can actually solve for that c value because we were given this initial condition right here, okay? And that's what I'm going to do. I'm going to get c as well from this. So here's how I do it. I say that, the v function, velocity function is negative 32 t plus c. Well, from my initial condition, I know that if t is equal to 0, then that means that I get 16 feet per second. So, as you can see, negative 32 times 0 is just going to be 0. So that means my c value is 16. So that means I can put a 16 in here now. And that is the velocity in this particular case. So maybe I'd write it out a little bit more explicitly here. V of t is equal to negative 32t plus 16. And that would be it for me. I'd just write it out like that and then circle it. You don't really have to include units, but I guess you can say it afterwards. So in, feet per second or something like that. I don't think I'd take points off if you didn't include that though. I don't think AP would either. All right, and then part B, find the height of the function. Well, the height in this case is going to be equal to the antiderivative of the velocity because height is just position in a vertical sense. So we're just, using that function that we just got and taking its antiderivative. Okay, so yeah, let's use it. So the one that we just found, v of t is negative 32t plus 16 dt. So for the antiderivative of that, we get negative, 32 divided by 2 is 16, t to the second, plus, and then it'd be 16t, and then plus some constant c. And just like before, we can solve for that constant value if we wanted to, and we're going to, because we have this initial condition where, oops, I didn't write that in properly. It's the initial height, so that'd be when t is equal to 0. H of 0 is equal to 64 feet. So if I plug that in here, h of 0, let me do it like I did before. H of t is equal to that equation there, negative 16t squared plus 16t plus c. And if I plug in 0 for t, I should get 64. So as you can see, all this stuff kind of just goes away because anything times 0 is 0. And that means my constant is also going to be 64 here. All right, so once I have all of that stuff, I can write out my function. So my function looks something like this. The height of the sandbag at any given time t is equal to negative 16t squared plus 16t plus 64. So that's my function. And then you can answer that in terms of it's in feet for your units. Okay, so easy enough. I didn't use the distance or displacement formulas, but still know those because those might show up on the test. Last problem, 25. A particle is moving in a straight line such that the x-coordinate of its position is given by that. So they give us position. They want us to find the velocity. Okay, that's easy because I know velocity is equal to the derivative of position. So that's all I got to do, just take the derivative. So negative 2t plus 4, that's it. And it doesn't give me any units, so that's my answer. So velocity is equal to that. Next up, acceleration for the particle. Well, acceleration is equal to the derivative of the velocity. So I'm going to take that same function that I just got, v of t, and take its derivative. So that's just going to be negative 2. So that means that the acceleration is always going to be negative 2 for the particle. All right, and then part C. At what time is the particle at rest? When the particle is at rest, that's when the velocity of the function is equal to 0. So I'm just going to take my velocity function, negative 2t plus 4, and set that equal to 0, and then solve for t. So if I add 2t to both sides, I get 4 is equal to 2t. That means that t is going to be equal to 2. So particle at rest when t is equal to 0. And then did it give us time units on that? Straight line such that position is given by that? Nope, it doesn't. So, time units, whatever units that it has. Okay, that's it for 25, and that's it for the review. So I hope this was helpful. If you need some additional help, go in and see your teacher. Thank you very much for watching. Hope you enjoyed them. Bye-bye.